Now we're going to look at the final two together. So the normal times the subnormal giving a subnormal, and the normal times a normal giving a subnormal. So we're really interested in when we get a subnormal result. So we've seen the little algorithm we run through. For this one here, we're going to have to change the unbiased exponent. So the unbiased exponent is going to be given by -126 minus the pre-leading 0 count. We're going to force the exponent to a value of 0 for the final result. And the mantissa is going to be a left shift by this amount here, which is the ex plus ey plus b plus 1. And again, this ex or the ey will be biased in this particular fashion above. And finally, we'll look at the normal times the normal given a subnormal. Now in this instance, we don't need to do this part here, so we just use the normal biased exponent. And then the final output, we force the exponent to a value of 0, and the mantissa is going to shift by this amount here. So let's go ahead and we'll open up a Logisim, and I've already worked through this design, so I'll read through the design and I'll show you exactly how I did this. So if you head into the resources section and open up the Logisim file, so it's called fpm underscore nnn underscore nsn underscore nss. Now we're actually going to do the final one in here as well, which is going to be the normal times normal giving a subnormal. Now if you head to the top level, so that's this one here, the test one, you click on that, it'll take you through here. Now you'll notice that the top level has changed a little bit, but what I decided to do was, rather than having the simple input, so originally we were sitting with an input like this and it had 32 bits, it would mean that we'd have to change these bits individually in order to put an input into the multiplier, and that's just not very efficient, and it just takes a long time and it gets really dull. So, well, first of all, I'll take away my image here because it's just cluttering this up for a moment. So what we have here, if I click on this, you'll see it's a RAM cell, and the RAM's going to be 8 bits wide, and it's going to have a data bit of path of 32. Okay. Now I've already used this previously, and in order to set it up, you could just copy what I have here, and you can work your way through. But the clock goes in here, okay, and we've set the load to 1 for this one, and the load for 1 to this, because we're going to load into these, okay, and we'll just leave the clear it set to just the earth, okay, to 0, and we've got an address coming in here. So this address here, what you do is you just count through the addresses. So if I was to right click on this and put in edit contents, you'll see that these are the contents of that RAM, and that RAM is going to have 16 different values here, and it's going to have 16 different values down here. So we're going to have 16 times 16, so you can put in 256 different numbers, and these here are the hexadecimal numbers. This is going to be this one number here is in effect our 32-bit binary number. So the first one is 4 bits, then that's 4 bits, and another 4 bits, and so on and so forth. So we're going to have 8 lots of 4 bits, which is 32 bits. So that's one number, that's another number, another number. So it allows you to put the numbers in directly. So I could actually go in here and I could just force these numbers to be whatever I want them to be. Okay, and then you could just close it, and you can see you would have that number in here. Now, in order to read the number in, you have to actually count it in. So you have the little counter that will actually just count the number into this RAM cell. So this is a little counter here, and I've just kind of squeezed it in a bit, but it's what we have is a counter, and you can see it's an 8-bit counter, and it counts up to the value of FF, which is 256, and whenever it gets to 256 it just stays at that value, so it'll just count up to that value and then just stop. And again, we just put in the clock here, so the clock is in here, and we can set up a value of 1 in here. I'm not going to talk your way through these individuals. You can get in here and put one down and you can test it out for yourself and you can see it working. And the clock, the actual clock is just sitting up here, okay? So this is a clock here, and I've just got the tunnel towards the clock. And the output of this here is the counting output. So as this counts up, it's going to work its way through these values. So you can see that here. If I pulse the clock, you'll see it jump into the next one, and then the next one, and the next one. So each time you can see I've arranged it so the address here also goes into the address here, and also goes into the address here. And you can see the output here, which is the multiplication of the x and the y. So this is the output here of these values. So we put the values in here, they come out here, and they come out here, they get in there and there, and they go through the multiplier, they come out, and then they go into this part here, and they're fed into here by the same clock. And this load is set to 0, so it's saying that we're actually going to load the values into this RAM here. So it means that as we work through the multiplication, it will take this number and this number, it will multiply it, and it will give you the output. And it will take this number and this number, multiply it, and it will give you the output. And it means that we can create a file of all of the outputs, and we can get a file of all of the inputs. And this is a good way for us to later on go ahead and create a testing script in order to test the multiplier more thoroughly. So let's go ahead and we'll have a wee look. Now we've seen that, we'll have a wee look inside the multiplier and we'll see what we've done different inside the multiplier. So you can see here that the multiplier looks really similar, but there's a few added extras, so let's talk our way through them now. So the first thing we've got to do, and it's the simplest thing, is ensure that if we have a subnormal output, it means that the exponent value here is going to be forced to all zeros. So rather than having the exponent value coming out here and going straight out, we have to make a choice. We have to say if the output is not a subnormal number, then we'll just have the normal output path from here, which would come out here and down into here. But we had to do a test for subnormal, so this little tunnel here actually comes from a test for subnormal, which we'll see just in a minute. Then if it is a subnormal, rather than having the output from here, we just force the output to be all zeros. So that's what this extra little mux in here is doing. It's just forcing the output to be all zeros for the exponent if we've tested and the output is a subnormal answer. So where do we do this test? Where does this test for the subnormal answer take place? Well, you can see it's actually taking place up here. You can see that the subnormal value comes out here. So this is the tunnel here. This point here is just connected directly to this point here. So let's have a look inside and see how we worked out this subnormal value. So you can see that there's an extra little bit of circuitry has been added here. So the top bit here tests whether the input is normal or subnormal, but the output, this part here, tests whether the output is normal or subnormal. So it's going to take a little bit of time to talk through this, and it's well worth our while going through it because it can create an awful lot of confusion. So if we think back to what we did previously, we've seen that if the ex plus ey, this is the unbiased exponent, if it's going to be less than minus 126, then we know we're going to have a subnormal number. In fact, if it's between the ranges minus 127 to minus 149, then we know we're going to have subnormal numbers. So we need to have a check to make sure that we're within that range. So let's go ahead and I'll open up the Excel spreadsheet and it'll become more apparent what we're doing whenever we look at this Excel spreadsheet. Now we need some method of ensuring that we understand whereabouts we are with our multiplication. So we want to know whether the answer is normal or subnormal. We would also in time want to know whether the answer overflows to plus infinity or whether it underflows to 0. So these are checks that we can see in the next video. But for this video, if we remember that we started off with an 8-bit range for the exponent, so that would mean that the exponent is going to range from either 1 to 256, or as we tend to deal with it, it's 0 to 255. So I've got 0 to 255 down here, so there's 0 to 255 and it ends here. And we've said that we're going to use a bias. Okay, the bias is minus 127. So whenever I take 127 away from 0, I get minus 127. So this gives us our negative range. So there's nothing new in that, it just means our range can now run from minus 127 to the plus 128. But the thing to note here is that whenever we're actually dealing in Logisim, we're actually dealing not with this biased range here, we're actually dealing with a signed decimal number. So for example, if I was to use the signed decimal for the 8-bit range, then our 0 would be a 0, 1 would be a 1, 2 would be a 2, so on and so forth, all the way up to the value of 127. But the value 128, so this is 128 in binary, is actually going to be minus 128 in the signed decimal, and 129 is going to be minus 127, so on and so forth. If you come all the way to 255, you'll see at 255 the actual value is minus 1. So you can see that we are going to get that because 255 is going to be equal to the, well, all ones, so it's going to be 1, 2, 3, 4, 5, 6, 7, 8 ones. But what happens with signed decimal is that the 255th bit, which is this bit here, or sorry, the largest bit, the 128th bit, is going to be this bit here. So what we do is we take that bit there and that becomes negative, and then we add on the rest of the bits here. Okay, so that becomes minus 128, and then we add the rest of this on here, which is 127. So that ends up becoming minus 128 plus 127 is minus 1. Okay, so this is how we're actually looking at it in terms of the signed decimal. Now, a thing to note as well here is that we've actually extended the exponent. So instead of our exponent running, and I'll get rid of these two columns now, okay, so I'll just hide that. So instead of our exponent, our range running from 0 to 255, it's now going to run from, well, it would run from 1 to 512, or equivalently, it would run from 0 to 511, okay? So this is a 511. So again, at 511, this would be minus 1. And if we work our way up through, you can see it getting larger and larger. And at some point, we're going to end up with the value of minus 126 here. So this is going to be 38, that's 385, that should be. Okay. So you can see here, at this point here, we're going to have our minus 126. So in order to ensure that we have a subnormal output, we have to have a specific range of values which tell us that. Now, the actual range in terms of our values that we're interested in are going to be values that are less than 126, but they're greater than minus 150. So that's actually within this little green range here. But this little green range here is in reality, in terms of the actual number that we're going to use, that is the actual binary number, or if you like the equivalent decimal number, are numbers which are going to be less than 386, so that's like 385, 384, and they're also going to have to be greater than the value of 362. Now, if we ensure that they're within this range, then we can be sure that we're going to have a subnormal output. So we have defined these numbers here in terms of their hexadecimal equivalents. So we really want this number here in hex and this number here in hex. So if I put that in hex, that's going to, I could put in equals dash to hex, and we'll click on this here, and that's going to be the value 182. And we need to check this one as well, so this is going to be decimal to hex again. I could just do Control C and Control V, and that's going to be 16A. So this is going to be our check then. We're going to check and make sure that the numbers that we get out are between these two hexadecimal numbers. So let's go ahead and I'll show you how I've done that. Now that bit's quite awkward, and it took me a little bit of time to work that out, and it's not really obvious unless you sit down and have a wee think about it. So take your time, a wee think about that, and if you like, you can always get in contact with me if you're not too sure. So you can see at the bottom here we've got the test for the subnormal output. We have our EX plus our EY coming in. This is our biased exponent, and we have to do two checks. First of all, we're going to have to check and see that the value coming in is less than the hexadecimal 182. So we've just said there that hex 182 is actually 386 in decimal, and the 386 in decimal is actually the minus 126 in the sign decimal for 9 bits. And secondly, we're going to have to check and make sure that the value EX plus EY coming in is greater than the value of minus of 16A in hex, which is 362 in decimal, which in our signed decimal for 9 bits is actually the minus 150. So we're just checking to see that we're in this number range. In order to check that number range, we actually have to use the signed decimal range here. So we're checking to make sure that we're less than 386 and greater than 362. So that will ensure that we are in the subnormal range. Now, if we're not in the subnormal range for the moment, we just assume we're in the normal range. So everything else out with it would be the normal range. But at some point in the next video, we'll add a few other sections in here, and one will be for an overflow to plus infinity, and one will be for an underflow to 0. So head up to this level again. Now we're going to go into the shifter, and this is where the biggest difference is. And we're going to take our time to read through this, because this is really the crux of how we shift the mantissa value. So we know that we've got 3 ways that we can shift the mantissa. We're either going to shift it left by a value of 0, which means we're just leaving the full stop where it is, or we're shifting it left by a value of 1. So we know we shift it left by a value of 1 when we have to normalise the result. But the other option that we have now is going to be a shift left by the xe plus ye plus b plus 1. So this is the third option that I've added in here. So let's have a wee look and we'll see how we actually work through these options. So I'll actually just change these numbers here and we'll see how we're going to get an output. So we've got 3 possible routes. So the first route is this route here. So this is the left shift by 1. So what happens here is we're assuming here that we actually have the most significant bit of the 48-bit multiplication as a value of 1. So we know when that is a value of 1, the full stop is actually sitting there. So we're going to have to normalise it by shifting the full stop 1 position to the left. So that will be the new full stop, which will be there. So it means that the value for our mantissa is going to start at this position, which is 1 position after the full stop. So it's going to be 1, 1, 0, 0, 0, 0. And you can see here that this value 48, this is the bit 48. So when I press this to 1, it's telling us that the value here for the most significant bit is a value of 1, in which case it's going to choose this route. And when it chooses this route, what we do with this route is that we simply cut off the most significant bit. So when we cut off that most significant bit, we're going to be left with our 23 bits, and we're going to have the correct mantissa, which is just going to start out with 1, 1. There you go, that bit's disappeared, we've got the 1, 1. So it's just a neat little way of killing two birds with one stone. We get rid of the 24th bit of the extension, and we in effect get the correct mantissa value. So that's one route that it can take. Now the other route that it can take is if this is a value of 0, then it will come through, instead of going through this route, it will go through this route here. Now in this route here, what happens is, if you see in this one, that we're assuming that the most significant bit is actually now a 0. So let's say the most significant bit is a 0 here. Then you can see that this is pulsed and we go through this route here. And what we can do in this instance here is that this is the correct position. This is the correct position for this is the correct position here for the decimal place. So it's 2 digits down. So this is the decimal point sitting here. But we don't need to move it up 1 to normalise it, because the value 1 is sitting right here. So it means that the actual correct mantissa just sits right of this decimal point. So it's going to be 1, 0, 0, 0, 0. So in order to get that 1, 0, 0, 0, 0, which you can see here, what we've done is we shift the value here left by 1, and then we get rid of the bit. So that's what I've done here. We've shifted everything left by 1, and then we get rid of the first bit. So this bit goes in here, this bit goes in there, and it gets cut off. And we're going to end up with that bit disappeared. We'll have our 1, 0, 0, 0, which is the correct mantissa. So we've already looked through these in the previous video. There's nothing new in this little section. We've already covered that. But we've got a third option available to us now. And this third option is whenever we've got a subnormal output. And when we've got a subnormal output, we want to shift the decimal point by the value xe plus ye plus b plus a value of 1. Now you'll note, if you remember, whenever we looked through the actual mathematics, that we ended up with not the value of xe plus ye plus b plus 1, we ended up with the negative value. And we don't actually want the negative value, we want the positive value. So in order to get the positive value, we've had to take this here, which has come from the bias point, and we take it away from 0. So we put a little subtractor in, and we take it away from 0 in order to get the positive value. So you can just ignore the fact that we've actually got a number -127 and +127. We wouldn't get numbers as big as this if we had an actual subnormal number coming in. The final output we would have had here with a subnormal number would be a number between 0 and 23. So we would be shifting it by as much as 23 places. Now there's one other thing to note here, is that I've changed this round slightly, because rather than using the decimal point as the anchor point, so this is the point between the 45th and 46th bits, we've always used that as an anchor point, and we've just shifted that point to the left. Now rather than doing that in this instance, it's much easier to use the 48th bit and then just shift the entire mantissa to the right. Now it's just simpler in order to realise it within Logisim, so it doesn't really matter whether you're moving the point to the left or moving the mantissa value to the right, the effect is the same. And what we can do is we can take the 48th bit and we can shift the entire mantissa to the right by this value here, which is the bias, and I'll show you where I got that bias from. So if you go in here, we've got the bias there, so that's going to be our ex plus ey plus the bias. So it's not the bias plus 1, I've taken it from this side here, so it's EX plus EY plus the bias. So if we take this, and remember this is a negative number, so we take that, we take it in here, and we put it through the negation here so it becomes a positive number. And what we can do is we can take that positive number, and remember here it's 8 bits, so we have to change it to a 5-bit in order to get into our shifter. And you'll note here the shifter's not a logical left, the shifter is a logical right, because what we're going to do is we're going to shift the mantissa value to the right, and when we shift it to the right we'll just include the values of the zeros that we require. So in effect we're adding in this number of zeros. So this is the EX plus EY plus the bias will give us the correct number of zeros that we require in order to give us the correct output for the mantissa. So that's another option coming out here. Now we can ignore this for the moment. This was what we used for our error correction, so we're not going to ignore that just for the moment. But you'll note here now we're going to have two outputs coming from here. Now one of them is going to be the top one here, right? But this one here at the bottom is when we have a subnormal output. So we'll need to have a choice whenever we come out on the top level of whether we're going to have a subnormal output or not a subnormal output. So again we'll go up to here and you can see I've tested that here. So we've got our two outputs coming out here. So one of them's going to have a normal output and the other one's a subnormal output. And we have to choose between them. And of course we choose between them using the sub value. So this tells us whether it's a subnormal number. If it is a subnormal number, then it will pass this value through. And if it's a normal number, it will pass either this one through or this one, depending on the value of the 48th bit. So there's been quite a lot in that, and this is really all the changes that have been made to it. Again, I haven't touched the rounding logic at all. We'll get into that in another video. So there's been quite a lot in this video. What we want to do now is just quickly go through an example just to show you it working. So I've ran up the multiplication tool. I've put a normal number in for x, which is this 10. I've put a subnormal number in. We multiply the two together, we get a subnormal result. So we can take these numbers here and we can put them into the Logisim simulation. So if you just make sure that you've got the little finger clicked here, and we can run through the simulation here. So we can click on this one, which is our x value, which is going to be 412, and there's going to be 5 zeros. 5 zeros, and the y value here, and you can click on this and it's going to be 0001166C2, and you can see here we get the output here, which is 000AE394, which if you check back in the simulation you'll see is the correct value. And you can head back down in here, and this is the way I think you should work out and ensure you understand how it works. If you put a value like this in and head back down, and then you can see how we generated each of the values. So we can come out here and we can see that the input here, x ends a normal, y ends a subnormal, and we can see that the output here is a subnormal output. And then you can check through the rest of the values through the tree here, and you can see here that if the values here are going to match up with what we have in the spreadsheet, and you can see here that the values we have are what we have in within the spreadsheet here. So that's all there is for this video. There was quite a lot in the video, and it's been on for nearly half an hour. I tried to keep them a little bit shorter than that, but we have gone through what we require to do for both other types of numbers, so whenever the output is a subnormal output. So thank you for listening. I'll get you on the next video. Goodbye.